This is Afe Ademola Johnson, your chemistry and biology tutor. Today we want to look at another way NECO calculation of titration. Question number 1, practical, can be asked, and how do we solve them? The first one we did was how to use titration to determine concentration. You can watch out for the video. In another video we did, we learned how to find the molar mass of a compound in which the Na has been replaced with letter X. We have X2CO3. Today we want to look at how they can ask us questions on solubility. And that is why we have the question on the board. A is a solution containing 1.05 gram of H2SO4 in 500 cm3 of the solution. And B was prepared by diluting 500 cm3 of saturated solution of Na2CO3 in 1000 cm3 of the solution. Put A into the burette and titrate it against 20 or 25 cm3 portion of B using methyl orange as indicator. Repeat titration for 2 or 3 more times until a concordant titer value is obtained. Tabulate your burette readings and find average volume of A used. Given the equation of the reaction as this. So let's try to titrate and see what we are talking about. The question says we should put A into the burette. You have to look for a beaker where they write A beside it. And look for your funnel. This is your burette and fill it up. Fill it up. So you release the jet to touch, for the meniscus to touch 0. Okay, good. We have done that. Then the next thing we want to do is to pipette, because he said titrate it against 20 or 25 cm3 portion of B. Now, the pipette we have here is 25 mil. 25 mil. So, and that is why before you tabulate your reading, write the size of pipette. It will carry its own mark, 25.00 cm3. So we want to use it to take B. So you look for the beaker that they write B, that is labeled B, and you pipette. You suck. Then you release. Then you take your conical flask, you release into it. Having done that, the next thing to do is to put methyl orange here. About 2 to 3 drops, and you see that the solution has turned yellow. Because sodium triiodocarbonate 4 is an hydrolyzing salt. It's a salt, it's a normal salt, but when it dissolves in water, it forms a mixture of triiodocarbonate 4 acid, H2CO3, and sodium hydroxide. So, and triiodocarbonate 4 acid is a weak acid. It ionizes partially to give little amount of hydrogen ion. But sodium hydroxide is a strong base, strong alkali. It ionizes completely to release large number of hydroxide ion. So in this environment, you have more of hydroxide ion than hydrogen ion. So the environment is what? Is alkaline. And that is why, and the color of methyl orange in an alkaline medium is yellow. That's why we have yellow here. So I want to titrate now. So you can see that the color has changed. You can see it has changed to pink, from yellow to pink. Then you stop and record your burette reading. In this place, I have 4.13. So because I fill this thing to 0, my initial reading here is 0.00. Then I now got 4.30. So if I take away this 0 from here, I still have 4.30. So I don't need to fill it again, I can continue from there. So my initial reading for the first title will now be 4.30. So that means in around if every 4.30 is required for titration, so I should get another color change at 8.6. Take note of that. So now I want to do the first title. So I want to pipette. Bubble should not be allowed. So I can transfer this into the conical flask. Then I put my meteor range. 1, 2, 3. So then I can titrate. So my color has changed. I told you this is a 8.1234. 8.4. Okay. So what I have now is 8.40. If I take this one away from here, 0 from 0, 0, 3 from 4, 1, 4 from 4, 4.10. So I have that. So you can see that the difference between 4.30 and 4.10 is 0.2. So it's a perfect one. So I still have enough. So if I add another 4 point something to this, around 12 point something or 13 point something, I should get another title. And this burette can carry 50 cm. So I can see, my initial reading can see the word 8.40. So now, let's titrate again. Then you use B to rinse the conical flask. Somebody should trash. Next thing, we want to pipette B. I take it here. So I take to my conical flask. Then having done that, I put my meteor range. So you can have the idea of where your color will change. Around 12 point something, I'm expecting the color to change. Now, the color has changed, and now we have, I read from here, I have 12 points 0.50. So that when I take this away from here, I have 0 here, 1, and I have 4.10. So if I see, I may decide to feed this to the 0 again, put more to here until it gets here and titrate again. So I can get something like 4.20. So take this one away from here, I have 4.20. So the next thing is to, I don't need my rough, I can cancel it, to find average volume of A used. What would I do? I will not use the rough, I will use first, second, and third. It will now be 4.10 plus 4.10 plus 4.20 divided by 3. So by my calculator, I have 4.1 plus 4.1 plus 4.2 divided by 3. Answer is 4.1. So I'm done with the titration. So the next thing to do is to answer the question. The first question, they say from your results, that is the table, and the information provided, these are the information, the equation, and all this information provided, and all the values in the questions. Find the concentration of A in mole per dm. But you cannot get concentration of A in mole per dm without first of all getting it in gram per dm. But what was said about A? A is a solution containing 1.05 gram. Gram is not the unit of concentration but the unit of mass. So for it to be taken as concentration, it has to be 1.05 gram per dm or 1.05 gram of H2SO4 in 1000 cm3 or 1.05 gram of H2SO4 in 1 gm3 of solution. That is when you will take it as what? The number as what? Gram per dm. But now that it is mass, gram that is here, you take it for mass. You will now standardize. You will now say 1.05 gram of H2SO4 is equal to, that is, it dissolves here. 1.05 gram of H2SO4 dissolves in 500 cm3. Then, what mass of H2SO4 would dissolve in 1000 cm3? Because a standard solution, where did we get this 1000? A standard solution is a solution whose concentration is known. And there are two types of standard solution. We have molar, a solution with molar concentration and a solution with what? Mass concentration. The SI unit of the concentration with mass concentration is gram per dm cube. That dm cube is 1000 cm3. So the mass that dissolves in 1000 cm3 is more recognized than the mass that dissolves in 500 cm3 according to the question. So we are looking for that mass that will dissolve in 1000, not the mass that dissolves in 500. So we now have what? 1.05 over x is equal to 500 over 1000. So 500 in 500, 500 in 1000, 2. So we have 1.05 over x is equal to 1 over 2. We cross multiply. X times 1 is x. Then 1.05 times 2. So our answer should give us 2.10, and now is what? Gram per dm cube. The question did not ask us to find concentration in gram per dm cube, but it just asked us to find concentration in mole per dm cube. But you need the concentration in gram per dm cube to be able to find concentration in mole per dm cube. And that is why you are going to use this formula. Concentration or molar concentration or molarity equals to mass concentration, mass conc, over molar mass. Over molar mass. Now, molarity is what we are looking for. That is concentration in mole per dm3. So the mass concentration is the one that has gram per dm3 as the SI unit, not gram. You can't use that one. So we now write it as what? We write it as 2.10 over molar mass of H2SO4. Don't forget that A is H2SO4. And H2SO4 has what? 2 hydrogen atoms. And 1 hydrogen atom here is what? Is 1.0. So I will have 1 to represent this hydrogen times these 2 plus sulfur is what? 32. Plus oxygen is what? 16. But we have how many oxygen here? 4. So we have 2.10. If you add this very well, you get 98. So our answer now is, you have 2.1 divided by 98. Answer is 0.021. Now, mole dm raised to power minus 3. That SI unit is very, very important. We have gotten that. Then, to answer question number 2, we are asked to find concentration of B in mole per dm3. We don't know concentration of B. We are going to use this formula: CA over CB VB equals to NA over NB. What is our CA? C means concentration of A in mole per dm3, which we have calculated now to be what? 0.021. 0.021 times what's our VA? V means volume of A, which is average titer value, which is now 4.13 over CB is concentration of B in mole per dm3 we are looking for. We write it like that. Our VB is the size of the pipette. That is the volume of B. That's 25.00. What's our NA? NA means mole ratio, number of mole of A. The question says A is a solution of what? H2SO4. So in the equation, H2SO4 is this. What did they use to balance the H2SO4? Nothing. It means there is an invisible 1 there. That's 1 over. Then B was prepared by diluting 50 cm of saturated solution of Na2CO3. So Na2CO3 in this equation now is B. So what did they use to balance it is 1. So I also have 1. So mind you, in this NECO, there's a bonus. Your mole ratio is 1 over 1. There's no contention for that. So what do we now do? We cross multiply. 25 CB times 1. 25 CB. This 25 is this 25. CB. Anything times 1 is that thing. Is equal to 0.021 times 4.13. So then we divide both sides by 25. CB is now 0.021 times 4.13 over 25. Our concentration in mole per dm3 will now be what? So we have 0.021 times 4.13. Answer is this. Then divided by 25, we have this. We have 0.003. Oh, okay. 3. 1, 2, 3. Okay. Now mole again. Your answer of mole per dm3, always make sure it is in 3 decimal places. We have done that. The next question is to find solubility of Na2CO3, and you want it in mole per dm3. Here we are going to use dilution formula. Using dilution formula. Dilution formula is C1 V1 equals to C2 V2. C1 means the initial concentration when the solution has not been diluted. The concentration. V1 means the volume occupied, the space occupied by the solution before dilution. C2 means the new concentration after you have added water to the initial volume. While V2 is what? The new volume after water has been what? Added. So Now look at the question. They say B was prepared by diluting 50 cm cube. So our V1 is 50 cm cube. Then our C1 is unknown. They didn't say anything about it. They just say B was prepared by diluting 50 cm cube of saturated solution of Na2. They didn't talk about the concentration it was, so we don't know it. Then our C2 is the molarity we just got, CB, our CB. So this one is same as the CB, which is same thing as what? 0.003 mole per dm cube. Then the last thing to look at here is what? Is V2. Our V2 is 1000 cm cube. That's final volume. They said B was prepared by diluting 50 cm cube initial volume of saturated solution of Na2CO3 in 1000 cm cube. So this is the final volume. So using our formula, substituting, in place of C1 now, we put the C1 because we are looking for it, times V1 is 50 is equal to C2 0.003 times 1000. So we now have this one the same as what? 50 C1 is equal to, then let's try to multiply this. It should give us something like 3 or 0.003 times 1000. Answer is 3. To divide both sides by this, divide both sides by 50. You have C1 equals to 3 over 50. Our C1 equals to what? 3 over 50. That is 0.06 mole per dm. So the solubility of Na2CO3 in mole per dm cube is what? 0.06 mole per dm cube. So we have come to the end of this lecture. So do not forget to subscribe and share this video and like it. And if there's any question or any way you want me to improve, you can put your suggestion in the comment section. If you have any question, put it on the comment section. And I remain my humble self, Afe Ademola Johnson. God bless you. Bye for now.